Welcome. So, before we get into definitions and diagrams, I want to start with a question that most courses never ask. What is a computer really? Not in the marketing sense, not in the spec sheet sense, but in the fundamental sense. What is actually happening when software runs on hardware? The answer is stranger than you think, and understanding that strangeness is what this course is about. The computer you think you're using does not exist. What you experience as a programmer is a clean, obedient machine. You write instructions, they execute. Results appear in order, predictably. But that machine is a carefully constructed illusion. Underneath your program, instructions are overlapping. Results are being computed out of order. Memory is not uniform. Some data is nanoseconds away. Some data is hundreds of nanoseconds away. And yet, your program behaves as if none of that is happening. How? That question is computer architecture. So let's be precise about what architecture actually is. Architecture is the definition of visible behavior. It tells software what is it that's allowed to assume about the machine, which instructions exist, how registers behave, how memory responds, what happens when something goes wrong. Notice what is not in the definition. Architecture does not say how fast things happen. It does not say how much power is consumed. It does not say how the circuits are built. Those are left deliberately unspecified because physics determines them. Signal delay, energy cost, thermal limits, reliability margins. These are not engineering choices, they are physical facts. Architecture exists precisely to mediate between what software assumes and what physics allows. Performance, power, scalability, none of these are handed to you. They all emerge from how well that mediation is done. So every programmer operates on a comfortable set of beliefs. Memory is uniform. Any address costs the same to access. Instructions cost roughly the same to execute. Run the same program twice and you get the same behavior. These beliefs are false, every single one of them. And here's the important part, they are usefully false. Without these illusions, you could not reason about a program. You could not debug. You could not build software at scale. The illusions are not bugs in how we think, they are load bearing fiction that the entire software world rests on. The hardware absorbs the costs of maintaining them so that you never have to see it until it breaks. And we will talk about when it breaks. So here's a concrete example of the illusion breaking. You run the same program, same binary, same machine 3 times, and you measure different run times, different power consumption, sometimes even different temperatures. A beginner thinks this is noise, random variation, something to average about. It is not noise, it is signal. It is the hidden structure of the machine leaking through. Cache state from a previous run, memory access patterns interacting with prefetchers, microarchitecture state that was not reset between runs. Performance variation is information. Once you understand architecture, you stop being confused by this. You start being able to read it. So here's the central claim, stated plainly. Software demands simplicity. Physics enforces constraints. Architecture is the negotiation between them. It is not an optimization trick. It is not a collection of clever hardware techniques. It is a systematic framework for deciding where to spend energy, where to tolerate delay, where to accept complexity, and where to push all of that cost somewhere the software will not feel it. Every architectural decision is a negotiated trade off. There is no free performance. There is no design that wins on all dimensions simultaneously. There is only the question of which constraints you're willing to live with and which ones you are not. That is what we are learning to reason about. So, one of the most important habits you need to build is being precise about which level you're talking about. These three words are used interchangeably in casual conversation. They should not be. Architecture is the contract. What instructions exist, what registers are visible, what the programmer can rely on. Microarchitecture is the machinery that keeps the contract. Pipelines, caches, branch predictors. These are not part of the contract. They are how the contract is honored under physical constraints. Implementation is where physics enters, circuits, layouts, process technology, the actual transistors and wires that make the microarchitecture real. Confusing these levels is how bad benchmarks get written, how misleading performance claims get made, how designs go wrong. Precise language is not pedantry here, it is engineering discipline. You might ask, why bother separating these levels at all? The answer is longevity and innovation. Because architecture is separated from implementation, the same ISA can run on a chip from 1995 and a chip from 2025. The software written for one works on the other. That backward compatibility is enormously valuable, and it is only possible because the contract is kept stable while the machinery underneath keeps changing. At the same time, because microarchitecture is free to evolve below the ISA, hardware engineers can pipeline more aggressively, add deeper caches, change the entire execution model without ever breaking a single line of software. The separation is what makes long lived ecosystems possible. It is one of the most consequential design decisions in the history of computing. So, let me show you the full picture. At the top, a problem. A human wants something done. That becomes an algorithm. The algorithm becomes a program. The program is compiled into instructions. These instructions drive microarchitectural activity. The microarchitecture is built from circuits. The circuits are built from devices. The devices are built from materials. So every layer in the stack hides the layer below it and creates assumptions for the layer above it. This is powerful. It is also dangerous. Errors at one level propagate upward in ways that are hard to diagnose. Constraints from one level propagate downward in ways that are hard to anticipate. Abstractions compress complexity. They never remove it. It is sitting there, underneath, waiting. Architecture sits at the narrow waist of the stack. Look at what is above it: an explosion of software diversity, millions of programs, hundreds of languages, countless algorithms, all of them making assumptions about the machine. Look at what's below it: an explosion of physical complexity, billions of transistors, kilometers of wire, quantum mechanical effects, thermal gradients across a die. Architecture is the point in the middle where these two worlds negotiate. Above the ISA, everything is logical and symbolic. Below the ISA, everything is physical and continuous. Architecture is the boundary layer between them. And this is why architectural decisions are so consequential. They are the last place where you can reshape physical cost without rewriting software, and the first place where software assumptions become hardware obligations. The ISA, the instruction set architecture, makes a very specific and deliberately limited promise. It promises instruction semantics, it promises register visibility, it promises addressing rules, it promises exception behavior, it promises memory ordering at some level. Notice what it does not promise. It does not promise timing. It does not promise energy. It does not promise how any of this is physically realized. The ISA promises behavior, not speed. This deliberate omission is what gives hardware engine designers freedom. It is what allows the same ISA to be implemented in a low power embedded core and a high performance server processor using completely different microarchitectures, and both have to be correct. The things the ISA hides are just as important as what it exposes. Instruction latency hidden. The ISA does not tell you how many cycles an add takes. That is microarchitectural freedom. Memory hierarchy hidden. The ISA presents a flat address space. What is in the cache, what is in the DRAM, what is being prefetched, none of that is visible. Parallel execution hidden. Your instructions appear to execute one at a time. Behind the scenes, dozens may be in flight simultaneously. Power consumption hidden. The ISA has nothing to say about joules per operation. Performance lives below the ISA line. Every time a hardware team improves a processor, they are working in this hidden space, doing more, faster, cheaper, while never changing the contract the software sees. Let me now describe the programmer's model precisely, because understanding it as a fiction is critical. In the programmer's model, memory is one flat space. Every address is equally accessible. Every instruction takes roughly the same effort. Execution proceeds sequentially, one instruction at a time, in the order you wrote them. This fiction enables reasoning, it enables debugging, it enables portability. But real machines must reorder instructions to keep execution units busy. They must buffer data to hide memory latency. They must speculate past branches before knowing which way they go. They must cache data at multiple levels to manage the cost of distance. Architecture exists to preserve the fiction while cheating underneath. The key tension, correctness, must stay visible. Performance may be hidden, that asymmetry is the engine of modern processor design. This leads to one of the most fundamental distinctions in all of computer architecture. Architectural state must always be correct. Registers, memory as defined by the ISA, exception behavior, interrupt state. If you can observe it from software, it must be right. Always. Microarchitectural state is allowed to be transient, approximate, even wrong, as long as it is corrected before it becomes visible. Cache contents, predictor tables, reorder buffer entries, speculative results, all of this can be wrong, discarded, rebuilt without the program even knowing. This asymmetry is what enables performance. The hardware can guess aggressively, speculate wildly, reorder freely, as long as it can always snap back to a correct architectural state when needed. The correctness guarantee is what the contract promises. Everything else is an implementation freedom. Now let's talk about what maintaining these illusions actually cost. Making software believe memory is uniform requires multi-level caches, coherent mechanisms, prefetchers, all of which consume area and energy. Making software believe execution is sequential requires speculation, rollback mechanisms, precise exception support, memory ordering hardware. Making software believe instructions are simple requires deep pipelines, bypass networks, and complex scheduling logic. And here's the subtle part: these costs are not independent. A branch predictor affects cache behavior. Cache misses affect pipeline occupancy. Energy constraints affect clock frequency. Every layer interacts with every other layer. Architecture is expensive because interactions are expensive, not because any individual component is. This is why building a fast processor is so much harder than it looks. Microarchitecture is where the engineering happens. The ISA is the what, microarchitecture is the how under constraint. Pipelines overlap work so that while one instruction is being executed, the next is being decoded, and the one after that is being fetched. Caches exploit locality, keeping recently used data close because there is a very high probability you will need it again soon. Branch predictors guess the future, resolving control flow before it is known, so the pipeline never has to stall waiting for a branch outcome. Buffers and queues hide latency, absorbing the time cost of slow operations so that faster ones can proceed without waiting. Two machines with the same ISA, that is, the same instruction set, same software compatibility, can differ by orders of magnitude in performance and energy. That entire difference lives in the microarchitecture. This is not an optimization detail, this is the main act. If a particular microarchitecture works so well, why does it keep changing? Because the constraints were designed for keep changing. When clock frequency was the dominant lever, deep pipelines made sense. More pipeline stages meant a shorter critical path per stage, it meant a faster clock. When power became the dominant constraint, that same deep pipeline became a liability. Too much energy per cycle, too much heat. When memory latency grew relative to compute, hierarchy and locality dominated design. The bottleneck moved and the architecture had to chase it. Architectural history is not a sequence of smart people replacing dumb decisions. It is a sequence of constraints moving and designs chasing them. Understanding this is what separates someone who memorizes microarchitecture from someone who can reason about where it is going next. Now, at the architectural level, nearly everything reduces to four coupled constraints: time, how long does something take? Cycles, latency. Energy, how much power is consumed per operation, per bit moved. Area, how much silicon is required, every transistor has a cost. And reliability, thermal margin, process variation, aging effects. These four constraints do not move independently. Faster usually means hotter. Smaller usually means more variable. More parallel usually means higher power density. Better reliability usually means larger margins, which means slower or larger. Architecture is the art of choosing which constraint to offend least, given the target application and the available technology. Here is the physical fact that has enormous architectural consequences. Distance costs money. When a signal travels across a wire, it charges the capacitance of the wire. Charging capacitance takes time. It also costs energy. The longer the wire, the more capacitance. The more time, the more energy. As transistors scaled down over decades, they got faster, but the wires connecting them did not scale in the same way. The results? At modern nodes, a signal crossing a large chip can take longer than the gate delay of dozens of transistors. The wire is the bottleneck, not the logic. This is why placement and hierarchy are architectural decisions, not layout details. When you put things on a chip matters as much as what those things do. Related to this and critically important, memory is physically farther from the compute than you might think. Registers are right next to the execution units. They are fast because they are close and small. SRAM caches are larger and slower because larger structures have more capacitance and longer internal paths. DRAM is off the critical path entirely. A DRAM access can cost hundreds of cycles, not because the memory is slow in some abstract sense, but because it is physically distant and moving data across that distance costs time and energy. Memory hierarchy is not a clever trick, it is a survival strategy. A single flat memory that was large enough, fast enough, and power efficient would violate multiple physical laws simultaneously. The hierarchy exists because the alternative is impossible. When someone says a processor runs at 3 gigahertz, does that actually mean? A clock cycle is a physical promise. It is a guarantee that every combinational path in the design, every signal that needs to propagate from one register to the next, will complete within that time window. That window must account for the slowest path in the design, plus margins for temperature, plus margins for voltage droop, plus margins for manufacturing variation. And this is why you cannot simply increase the clock and get more performance for free. A faster clock means a shorter window. A shorter window means some paths that were meeting timing no longer meet it. You have to redesign, shorten paths, add pipeline stages, spend area and power. Clock period is a physics limited promise, not a dial you freely turn. For decades, the free lunch was frequency scaling. Each new process node, transistors got smaller, they switched faster, and dynamic power stayed roughly constant because the voltage also dropped. The last part stopped being true. Dynamic power scales with capacitance times voltage squared times frequency. When voltage stopped scaling, increasing frequency meant increasing power quadratically. The chip got too hot to run at those speeds continuously. At the same time, leakage current, which was negligible in older nodes, became significant. Even idle transistors began consuming power. The result was a fundamental shift. The era of frequency scaling ended. The era of parallelism, specialization, and efficiency first design began. Every multi core processor, every domain specific accelerator, every power gating scheme you see today is a direct architectural response to this physical reality. This shift changed what architecture is fundamentally about. For decades, the primary question was how fast can we go? Today, the primary question is how long can we sustain performance within an energy budget? Energy is now a first class architectural constraint. It determines battery life in mobile devices. It determines how dense you can pack compute in a data center before hitting thermal limits. It determines whether a chip throttles under load. Performance that cannot be sustained is not performance, it is a burst. Every architectural decision now lives under an energy budget. Instructions draw from it, memory accesses draw from it, speculative work that gets thrown away, true from it, and got nothing in return. Designing for energy efficiency is not a secondary concern. It is the central engineering challenge of modern architecture. There are only two things a computer fundamentally does: it computes, transforms data through logic operations, it communicates, moves data from one place to another. What surprised the field and continues to shape architectural thinking is how asymmetric the costs of these two activities have become. Arithmetic got cheap. A floating point operation in a modern processor costs a trivial amount of energy. Moving data did not get cheap. Moving a value from a register to an L1 cache costs more than computing on it. Moving it from DRAM costs orders of magnitude more. Moving it off chip costs more still. This inverts the intuition most people have about what computation is expensive. The dominant cost is often not what you compute, it is where the data lives when you compute it. This asymmetry can be made concrete. Energy per arithmetic operation has improved dramatically over decades. Compute has scaled well. Energy per bit moved has not improved at the same rate. Each boundary crossing, register to cache, cache to DRAM, chip to off chip memory, carries an energy cost that scaling has not eliminated. The architectural implication is direct. Reuse beats raw compute. If you can keep data close and use it many times before moving it, you win. If you bring data in from the DRAM to use it once, you lose. This is why modern architectures are obsessed with locality, with blocking and tiling computations, with scratch pads and explicitly managed memories, with accelerated designs that minimize data movement. Energy scales with distance far more than with arithmetic. Let me make the distance argument even more explicit. Physical distance on a chip rough directly translates to capacitance. Capacitance must be charged and discharged to move a signal. Charging capacitance causes energy and takes time. No amount of clever circuit design eliminates this relationship. It is dictated by physics. Abstractions hide distance from software. The programmer sees a flat address space. The hardware sees a topology with widely varying costs at different locations. The hardware pays for every distance the software ignores. This is why hierarchy, tiling, and partitioning are not just performance tricks. They are spatial optimizations disguised as logical ones. People sometimes ask, why not just build one large, fast, unified memory? The answer is that such a memory would violate multiple physical constraints simultaneously. Large structures are slow because internal paths are longer and capacitances are larger. Fast structures are small because speed requires proximity and minimal capacitance. Low energy access requires the data to be nearby. You cannot simultaneously have large, fast, and energy efficient. The hierarchy is not a design preference. It is not engineers being clever for the sake of it. Uniform memory is a software convenience, not a physical option. Hardware enforces the illusion of uniformity so that software can program to a flat model, while the hardware quietly manages a deeply non uniform physical reality. When architects evaluate design, they reason in terms of five metrics: latency, the time for a single operation to complete; throughput, how many operations can be completed per unit time; bandwidth, how much data can be moved per unit time; energy per operation, how many joules each operation costs; and area, how much silicon is required. Every real design decision shifts several of these simultaneously. Improving one almost always worsens another. The skill, and this takes time to develop, is knowing which metric actually limits your system and refusing to optimize the others prematurely. Architecture is multimetric optimization, not a single number tuning. High bandwidth does not mean low latency. A wide pipe can still be a low pipe. High throughput does not mean a fast response. A system can process many requests per second while each individual request takes a long time. A higher clock frequency does not guarantee faster programs. If the program is memory bound, the clock is not the bottleneck. High tops, tera operations per second, does not mean useful work is being done efficiently. TOPS measures theoretical peak, not what your workload actually achieves. Misused metrics are worse than no metrics because they give you false confidence in the wrong optimizations. Always ask which metric is actually constraining my system right now. Performance is governed by bottlenecks. If one stage of a pipeline dominates execution time, improving anything else has negligible effect. If memory bandwidth is a constraint, adding more compute units does nothing. You optimize the bottleneck or you waste effort. Bottlenecks also move. Fix one and the next one reveals itself. This is not frustration, this is progress. A system whose bottleneck has moved is a system that has been improved. The discipline of architecture trains you to ask one question before any optimization. Where is the time actually going right now? Not where you think it is, not where it used to be, right now. That question guides every meaningful design decision. Good architecture begins with accounting. Execution time must be decomposed, attributed, and explained. Before you can argue how to save time, you must be able to explain where it went. This is what separates engineering from folklore. In folklore, you add a cache and things get faster, and you're not entirely sure why. In engineering, you know exactly what fraction of cycles were lost to memory latency, and you can predict with reasonable accuracy how much a given cache size will help. Performance is not guessed, it is budgeted. If you cannot account for time, you cannot improve it. All of this leads to a simple but powerful model that you will use throughout. Execution time equals the number of instructions times the cycles per instruction times the clock period. Each term belongs to a different level of the stack. Instruction count is influenced by algorithms, compiler choices, and ISA design. Cycles per instruction is determined by the microarchitecture, by how well the pipeline is utilized, by cache hit rates, by branch prediction accuracy. Clock period is set by circuits and technology, by the critical path delay and the margins required. Architecture is the discipline that connects all three and understands how a decision at one level ripples through the others. This model will reappear throughout everything we do. You might expect that as systems get more complex, the models we use to reason about them would need to become more complex too. That is not what happens. A small number of simple models, the performance equation, hierarchy thinking, bottleneck analysis, keep reappearing across decades of architectural change. They survive because they align with physical reality. They capture the dominant costs while ignoring detail that does not matter at the level of design decisions. Complexity accumulates on top of these models, not instead of them. When a model stops matching reality, it gets refined or replaced. When it continues to explain behavior, it endures. Good models survive because physics does. The risk versus risk debate is often framed as a philosophical argument about instruction set design. It was not. It was an accounting decision. Complex instructions seemed attractive. One instruction could do the work of many. But those complex instructions increased decode cost, made pipelines harder to build, raised verification burden, and made clock scaling harder. Simpler instructions enabled deeper pipelines, faster clocks, more predictable execution, better energy efficiency. The cost moved from hard software, where compilers had to do more work, into hardware, where it could be amortized across billions of transistors. Risk won because it respected where the real costs were, not because simplicity is philosophically virtuous, but because at the physical level, complexity in the ISA was being paid for in the wrong currency. Here's the thing about risk though, complexity never disappears, it migrates. When instruction sets became simpler, the complexity moved into the microarchitecture, branch predictors, out of order execution engines, reorder buffers. All of this complexity exists because the ISA got simpler and pushed the work somewhere. When hardware became energy limited, complexity moved into software scheduling and workload structure. Compilers had to become smarter, programmers had to think more carefully about memory layout. Today, complexity increasingly lives at the system level. Architecture is largely about deciding where complexity hurts least, not about eliminating it. For a long time, architecture quality was somewhat masked by process improvements. A clumsy design from one generation would be competitive simply because the next node was faster. You could get away with it if transistors kept getting cheaper and faster. When frequency scaling stalled and energy dominated, those masks fell away. Suddenly, decisions about locality, parallelism, memory hierarchy, and specialization mattered enormously. The gap between a well architected design and a poorly architected one stopped being hidden. Architecture did not return because it was forgotten, it returned because it was unavoidable. We often talk about CPUs as general purpose processors, as if general purpose is a fixed category. It is not. General purpose, GPU, accelerator, these are points on a spectrum defined by flexibility, latency tolerance, and efficiency. A CPU is highly flexible. It can run any code, but it pays a higher energy cost per operation because of all the machinery required to support that flexibility. A GPU tolerates high latency on individual operations but achieves enormous throughput by running thousands of threads simultaneously. An accelerator gives up flexibility almost entirely but achieves orders of magnitude better efficiency for a specific computation it was designed for. General purpose is a position, not a category. Every design chooses where to sit on the spectrum, and that choice reflects assumptions about what workloads matter and what constraints dominate. Every architectural decision trades something away. Lower latency often costs energy. Higher throughput often costs area. Greater reliability often costs performance margins. No knob in this space moves independently. Pull one and the other shift in response. Good architecture does not eliminate trade offs, it makes them explicit and defensible. A good architect can tell you exactly what was sacrificed to achieve each design goal and why that sacrifice was the right one given the constraints in the target application. A bad design is one where the trade offs were not understood and the costs appeared as surprises. Now, with this perspective, here's what you are now equipped to do. You can explain why systems behave the way they do, not just observe what they do. You can predict where performance will collapse before it happens by reasoning about which constraint is binding. You can recognize misleading benchmarks because you know which metric is actually being measured and which ones are being ignored. You can evaluate claims critically. When someone says their chip is 10 times faster, you know the right questions to ask. This is not about memorizing structures, it is about reasoning from constraints. That skill transfers across every generation of technology. Let's return to the abstraction stack, but now annotated with what we have learned. Every downward step in the stack increases cost. Time cost because physical paths get longer. Energy cost because more capacitance must be charged. Distance cost because signals travel farther. Architecture lives exactly where those costs become visible, but are still manageable. Above architecture, cost is hidden inside software abstractions. Below architecture, cost is hidden inside circuits and physics. At the architectural level, you can see both sides clearly and make decisions that affect both. This diagram is not background material. It will quietly govern everything we do for the rest of the course. So let me restate the central idea one final time cleanly. Software asks for simplicity. Physics enforces reality. Architecture negotiates between them. Every cache, every pipeline, every predictor, every queue exists for one reason: to preserve the illusion that the machine is simple at a cost that is acceptable. When the cost grows too large, the illusion weakens. Cache misses become visible. Thermal throttling becomes visible. Memory latency becomes visible. And software must adapt. Architecture is the peace treaty between abstraction and physics. It is a treaty that must be renegotiated every time the constraints change. In a world without free scaling, every architectural choice shows up directly in products. Battery life, tail latency, thermal throttling, cost per operation, these are all architectural outcomes, not accidents. A decade ago, you could build a mediocre architecture and let the process node carry it. That era is over. Understanding architecture is no longer optional if you want to reason about real systems. It is the primary lever available for improving performance, efficiency, and capability going forward. So, if architecture manages time and energy, then the natural next question is obvious. Where does time go inside a CPU? What does one instruction actually do from the moment it is fetched to the moment its result is written back? How does a clock shape behavior at the level of individual operations? To answer that, we need to open the machine, but gently. In the next lecture, we will build the minimal CPU. No speculation, no caches, no cleverness. Just enough structure to see how instructions, state, and time interact.